So good morning and good afternoon. So thank you for joining seminars. So this is actually the second seminar in this year, but I think it's more than 100 times as a I²CNER seminar. So my name is Tsuyohiko Fujigaya. So I will chair this session today. So today we welcome. I'm very happy to invite Professor Yang. So before starting the seminar, so I want to ask Petros to give a few words for us.
Yes, thank you very much, Professor Fujigaya. Again, long time not seeing you. Thank you. This is a great opportunity. Those webinars bring us together, and thank you for giving me here the floor, right? And I would like to start by saying first, good morning to our friends all over Japan. Good evening to our friends here in the United States, to Europe, to Australia, everywhere in the world, because this is an internationally attended seminar. And I would like to give just a few words and say that at I²CNER, our vision is to contribute to Japan's and the world's quest for a sustainable and environmentally friendly society. Working toward this vision, we carry out fundamental research to enable the development of low carbon, high efficiency, and low cost energy systems that will help Japan on its way to carbon neutrality by the year 2050. The execution of this mission of I²CNER towards this carbon neutrality is partly carried out by our webinar series and the types of the presentations that you are about to attend. Again, I'm always very pleased to say that through this webinar series, we engage each other in active discourse. We find and establish new research connections and live in the end with an excitement and motivation for scientific discovery towards our common goal of the carbon neutral energy society. So without further ado, I would like to turn it over to my colleague, I²CNER Principal Investigator, Professor Fujigaya, to introduce our distinguished speaker today, who happens to be my colleagues here at the University of Illinois. Professor Fujigaya, the floor is yours.
Okay. So thank you, Petros. So before starting, so after the Professor Yang's talk, you can ask a question. So you can use a Q&A function in the webinar. So okay, so let me introduce Professor Yang. So as you already know that he's a very distinguished professor from the Illinois, and he received a bachelor in Tsinghua University. This is one of the best university in the Asia. So and he moved to the Canada, Toronto, and he got a PhD degree in Toronto, and did a postdoc in Harvard, and then launched his individual research group in Rochester in 2001, then moved to the Illinois. I think this is correct. And he became a full professor in 2012. Okay. So now he is many editor. He works as an editorial board in many journals. So I think you may know him. So okay. So today the title of his talk is recent. Oh, okay. You can share your screen first. So recent development of a complex metal oxide electrocatalyst for oxygen evolution reaction. So okay, Professor Yang.
All right. Good morning. Good evening.
Oh, this is opposite.
Oh, just 1 second. Let me hide some of this stuff. All right. Okay. All right. Let me just move this away a bit. Yeah. Good evening and good morning, everyone. First, let me thank Petros for the kind invitation. Also, thanks Professor Fujigaya for hosting this event. It's a great honor. So I moved to Illinois right at the I²CNER was established, I think. And so this is my 10th years in Illinois. I think it's probably I²CNER established probably around 2011-ish. So I'm very glad to interact with many folks, and thanks to Petro's effort, I actually visited Kyngshu a couple of times, I think either 2 or 3 times in the past. And in fact, my last travel before COVID was visiting Kyngshu University. And so that was a fun time. So I hope we'll have more opportunity to do it in person, either in the US or in Japan. So today I'm going to focus on the discussion of complex metal oxide for oxygen evolution reaction. And this summarizes some of our most recent effort related to the sustainability and hydrogen technologies. And so to this audience, probably not, I do not need to, let's say, give a long introduction. I just want to bring a little bit tidbits here to just to remind everyone that even at the Champaign, with only slightly over 100,000 population in the Champaign and Urbana twin cities, we also have hydrogen-powered buses. Not only that, we also have the hydrogen generation station based on the solar. So that tells you the impact of the technology and how far it had been developed since the early days, possibly about 2 decades ago. That's where the hydrogen technology started to emerge in everybody's radar screen. So there are a lot of advantages. So the advantage of hydrogen fuel, they have high energy densities, high efficiency. Of course, refilling is also a very nice feature of it. So in that respect, that U.S. in the past, let's say, decades also actually fall behind in terms of investment and internationally. So this is the hydrogen strategy chart that presented last year at the Earthshot, or the hydrogen shot presented in the United States. Well-established places that in Europe, this is all based on the hydrogen technology, i.e. hydrogen utilization in various areas. U.S. only started the major investment last year, i.e. at the $9 billion level. So before that, of course, there are still a lot of investment, but at $1 billion investment, and that started last year. So I hope in the next few years, the U.S. will catch up with the international pace in the sustainability developments. So today I'm going to only focus a small part of my most recent work and throughout. So I'm going to primarily focus on the electrocatalysis developments. And the other part of our research, i.e. the nanoparticle formations, and how do we use the alloys or intermetallic platinum-based system for OR reduction system or OR catalyst will not be covered. So I'm going to primarily focus on the oxygen evolution reaction and primarily targeted for hydrogen production from water electrolyzer. So that set up a tone. But even before that, I still want to mention a bit on the oxygen reduction catalyst development side from my lab. So in the next few slides, I'll just quickly go over that before I go into the oxygen evolution reaction catalyst development. So we have worked on the oxygen reduction reaction quite well. So primarily focus on the low PGM catalyst and develop different type of faceted nanoparticles and use them as the catalyst. Primarily based on the principle of faceted particle process, certain surfaces, and those surfaces has preferred oxygen reduction catalytic activity. So of course, our niche area is always in that space, primarily in the processing, i.e. making catalysts with those specific features. So those early work lead to us to focus on most recently, specifically on the, let's say, intermetallic based system, i.e. the intermetallic cobalt platinum based system, for a simple reason, because we want to have a higher power system, i.e. for the truck or the other aviation system of the hydrogen fuel cell. So in that space, you need to have high loading, high stability systems. So we try to develop those type of intermetallic based catalysts with a high dispersion on carbon support. And there are a few approaches we took, including using the points of zero charge as a tool to regulate the formation of nanoparticle, get to the proper composition, i.e. the proper platinum cobalt based metallics, and then convert that into a proper intermetallic phase, and as evident in this diagram, i.e. the L10 platinum cobalt phase, that kind of let's say study. And also, as you can imagine, the particle we focus are typically rather small, around 2 to 4 nanometers, and try to maximize the formation of this intermetallic. And there are fundamental issues in terms of how stable those intermetallic could be, approaching this almost the limitation of these particle size. The other aspect we also venture into in the oxygen reduction catalyst part is the development of non-platinum group metal catalysts, and primarily focus on the single atom development. And this is related to so-called the MOF-based, i.e. metal organic framework based, or we can also call it atomically dispersed precursor-based synthesis. And so, i.e. this is the idea for that. So let's move on to my talk for today. So focus on the water electrolyzer catalyst development for the hydrogen production. So currently there are two types. That is, one is acidic electrolysis, and the more popular one at the moment is the alkaline-based system. So depending on the skill and also the efficiency or the other benchmark, so people either choose alkaline-based system, i.e. for development, or more importantly, the current industry, the green hydrogen production, primarily still based on the acidic condition. So there are many issues. One of the key materials development requirement is the oxygen evolution reaction, as being highlighted in this red box. And that we start from water that can generate hydrogen and give out the electrons. So an anode side, which we may not have a lot of slides, a lot of efforts, and so it's also related to oxygen evolution, but this is primarily from the alkaline. So primarily it's involved in the hydrogen, oxygen, and most commonly see is oxygen metal catalyst development. Okay, so how do we get into this area, and why we took the particular approach of using the complex metal oxide, i.e. the AB2 metal, plus the oxygen. So in comparison, the industry system always related to the OER is either iridium oxide or to much less extent the ruthenium oxide, primarily due to its stability consideration. So this is the earlier work, right around the time I moved to Illinois, i.e. the pyrochloride, the perovskite metal oxide OER catalyst being reported by MIT group that demonstrated you can have a lanthanide based different kind of a composition and lead to a very different performance. And so this is tested at the fairly relatively low current densities, but show a very nice trend that give you a different kind of over potential. For example, if you're dialing, let's say cobalt change to manganese, or you can choose B sides, also change to different metals, you have the property changes as well. Of course, after the decade, we must have learned a whole lot for these systems. We know the system become more and more complex, maybe just not as simple as we originally thought, but this is really a new system for us to start thinking about how can we start to look into A-side, B-side metal for a system and look at the performance of it. So in the early days, in this particular case, for instance, the argument there is you can tune the electronic structure of the B-side metal. So on the right-hand side, you can see the mechanism being proposed. And so there is this valence change, i.e. you can see the B sides can change from, let's say, N+1 become N+. And at the same time, you can see the O group, i.e. the oxygen change from OO to minus, change to OH group, and so on and so forth. Of course, this is based on the alkaline system, so you can see there's an OH group involved, also the other intermediate involved. So the open question for us then is that, can we look into the system? This is a very nice tunable system, because if you think about this, right, so you have A sides and B sides, and the tunability is tremendous. And I also kind of inspired by the use of perovskite, because based on my prior experience, I know the perovskite have a lot of the variable parameters that you can dial into it and still maintain the generic structure. And there is tolerance of defects in the system. So that means we can dial in different level of electronic intensity of certain binding sites, all change the oxygen. So at that moment, I like to think, since this is oxide, I like to focus on whether we can start to control the oxygen, right? So that could be a quite interesting aspect. So first things I was thinking about is, can we start thinking about the oxygen deficient structure? This will change the valence or the covalency of the structures, as well as the potentially lattice defect or the accessibility of the sites that are interested of, for example, the B side, for instance. So what about the other type? So the other defect type of perovskite related to this is the pyrochloride. So today I'm going to talk about all of them and give you an example, primarily focus on the site tuning and the OER performance correlations. And so there's a few of those examples that we did in the past 10 years, and also some of the recent work focused on the B side tuning in particular, we published in the recent time. So we're going to have a blend of some of 5 to 7 years work to our most recent work. So we started by looking at the this A2 B2 type of structure. So there is a few advantage of this. So clearly there is the advantage of having, let's see what I can have. Okay, great. Let's see, clearly you can see that there is this chemical stability is in the consideration. Of course, the stability is in the consideration. And also the oxygen vacancy being introduced, and we speculated at that point that could help to the performance. So plus on that, you can have using sites as a specific purposes and to look at the performance. So i.e., for instance, Basal will be the oxygen binding site, and that could lead to the development of different type of catalyst behaviors. On top of that, you can start thinking about, even though they have the same electronic structure, the radius could be different. That also could lead to the stability changes of the oxide. So can we really start thinking about both the activity and stability at the same time? On top of that, then if you have this AB2 oxygen complex oxide, the range of conductivity in it, it could range from insulator to semiconducting to metallic features. So what that kind of, let's say, structure feature due to the OER performance, that is still something that still actively researched in the community. So that's how we start thinking about that particular kind of angles. So our first target compound is actually, we did a comparison study focused on the calcium manganese oxide in that particular case. So in this calcium manganate system, we compare the calcium manganese perovskite. Indeed, they show both the activity enhancement, i.e. the calcium 2, manganese 2, oxygen 5, this oxygen deficient structure allow the mobile of oxygen or the defect generation being favored. So you can look at both cases that work out really well. So we did a little bit more careful consideration. So what is intrinsically make this catalyst better than the perovskite, i.e. the oxygen 3 catalyst phase? Of course, there is oxygen defect, so there is this sites being opened up. So there will be the intrinsic lattice oxygen vacancy that we're favored. For the electronic configuration of the cation, i.e. the B size metal, because the change of oxygen that also lead to the change of cation center changes as well. For instance, in this case, if it's 2.5, i.e. A to B2O5 structures, we can have the so-called high spin state, i.e. the EG orbital will be single occupancy. So that turns out to be a feature that electronically favor the OER performance and being, let's say, proposed and illustrated in the science paper I mentioned earlier. So this is turns out to be a win-win situation. Not only will be open up the oxygen lattices, but also change the electronic stage. So these are the two features at a time we think what goes on in this particular type of complex oxide structure and why it helps in terms of at the structural level, the oxygen evolution reactions, i.e. instead of having the knockoff at the octahedral site on the surface, and it's going to naturally have a lot of these sites could be already available on the surface as well, i.e. could be favor the absorption of the active group or linked to the, for example, the OH or OH group on the surfaces. So that's why we're very, very early thought about this particular system. As you can see, this is what we try to see here. And to summarize this particular work, is that the role of oxygen in OER catalysts become kind of quite pronounced. So instead of only focus on the sides of the metal sites, now we're thinking about the correlation of all these oxygen defect structure that what happens if you have these different type of metal sites being changed. So you will see in the following presentation, there will be this discussion on both sides, the electronic impact on the performance, as well as nowadays that the emerging new theory, so-called the lattice oxygen mobility mechanism, that also contribute to the overall performance. So now you will see if you analyze, at least this is a two competing mechanism for the oxygen evolution reaction. And one of them, of course, is the so-called the absorbate evolution mechanism. This is one I propose. You will see the being proposed earlier, focused on the electronic structure primarily. But for the lattice oxygen, in this case, the main difference, if you compare this to, for example, that this empty oxygen site can be being replaced and be mobile. Okay, so this oxygen can participate in the reaction. So by having this mobile oxygen, and the quantum simulation result based on the AEN system, I typically predict let's say the OER over potential around 300 millivolts, and could be even further reduced, which has been observed quite well since like maybe decades or two ago. Now we have a theory kind of contribute to the understanding of this phenomenon. And so this is basically lattice-based. That's based on the introduction of oxygen and vacancies. And if you have this vacancy being generated in the system, it's supposed to be beneficial. So on that note, so I'm going to show a few examples that we have worked on in the past several years, that including, let's say, the case of pyrochloride. We're still working them very, very hard in our laboratory. I'll show you an example, and also going to show you another example that can use the principle to extend to a different kind of structure called the reticent pulper phase, with the perovskite layer and some other intermediate layers in between. So that kind of structure as well. So I don't think I have a time to do in the spin now, but it's an emerging new class that hold the potential to make a more stable and highly active catalyst for oxygen evolution reactions. So how do we get started with the pyrochloride type? Besides the original, let's say, evaluation, try to introduce defect or either vacancy type or the excess oxygen in comparison with the perovskites. This paper is actually kind of inspired us to some extent. This is from CEDAR's work that focus on lithium batteries, and they have mapped out a different type of solid state type. And it turned out this A2B2 side, the oxygen 7 type, is one of those. So we're looking for possible stable structure to begin with, so that's where we got started. So we choose this particular system, and more importantly, we start looking to the as acid-based media. And so in the remaining time, most of the OER catalysts I discussed will be in the acidic media. Okay. All right. So one of the challenge, of course, is the stability. So in the early days, this is from Linda Laser group, also focused on the battery development, and also interested in making the pyrochloride type of solid and use as electrocatalyst. And they try to use the mesoporous structure to do it. And there is this challenge to making that into a mesoporous structure while it's very stable. So it turns out that mechanically, this kind of structure is not that stable, so that leads to a lot of issues. So we are kind of enter into the area thinking about develop a stable catalyst, focus on, let's say, E-train-based system, among others. Okay, so in the early work, of course, we have to test out a variety of pyrochloride structure. We actually, in the first batch, we test about 20 to 30 different kinds. And this is the one that is being screened out with a decent stability, also very nice activities. So here's what we observe in this particular system. This using ruthenium oxide as a reference catalyst. If you compare the E-trans ruthenium oxide, the pyrochloride structures, doing the simple CV test in comparison with the ruthenium-based system, you can see if you do 1 to 10,000 cycles, the ruthenium-based system is very stable, but the ruthenium oxide is down. So there has to have something that the E-train does to the system. Okay, so this is our first system, and also the thought process goes into design of using A side to control the B side properties. So we look into a little bit more careful about what happened in this particular system, and in terms of valence of the ruthenium side. And we did actually absorption spectroscopy, examine the near edge, and also do the XF. From the XF, we know that if you compare it, we can see that we do not have the major, let's say the major differences. But if you look at the valence side in the zinc type of catalyst analysis, referenced to the zero valence of ruthenium foil metals versus ruthenium oxide. And we actually reference somewhere in between that. So that means we have non-stoichiometries of the ruthenium side. Okay, so that always being, let's say, indicated can be a catalyst with higher activities. And how about the stabilities? So we did a simple partial DFT calculation, density function theory calculation, and try to look into the E-train impact on the ruthenium oxygen bond. The idea there to see whether by having the E-train, we can strengthen the E-train ruthenium bond strength. And this is an assumption still being made, i.e. the ruthenium is the active site for the metals. And it turns out if you do the DFT calculation, the overlap between the P band of the oxygen and the ruthenium D band orbitals is actually downshifted. This is being summarized on the right-hand side of this image. And if you look at the orange color ones, so it downshifted in comparison to the ruthenium oxide, this is the E-train, and by 0.4 EV. And so this, what we think is contributing to the stronger ruthenium oxide bond and the overall stability. So with that, we also look into the relevant system of a Uridine oxide-based system. So in this particular system, so we also observe the higher performance with respect to Uridine oxide. In this case, what we think goes on in this particular case and could also relevant to the electronic configuration once we have the E-train being added in. So in comparison with the pure, let's say, metal oxide of a Uridine oxide, and the the so-called bridging ratio value increase, and that typically symbolizes the higher the orbital spin and coupling. So this could lead to the split into orbital splitting and generate the single pair electron on the uppermost orbitals, and with a similar electronic configuration as the EG orbitals. So this could fall into the category of electronic configuration-based property enhancement. So of course, this is all based on the box system analysis, and so the surface could be different, but this at least offer a way looking forward what could happen. So at that point, we also thinking about looking at the opened up the pores of the OER catalyst. The way to do it, and this is a traditional way to think about this, of course, is thinking about the mesopores structure using templated approach. So this could be generated using micellar structure or lytropic liquid crystal as being demonstrated in the previous case. And so what we have found out is that we can also generate by having the porogen. So in this case, is the pyrochloride, pyrochloric acid. If you use pyrochloric acid in this particular system, we actually can generate this very porous, literally this ceramic type of structure made of yttrium, ruthenium, the oxygen. So this is a porous structure. As you can see, the medias, they connected through the primary particles. The other thing come to our attention, and actually we're struggling at the beginning, try to figure out what's going on here, is that it turns out to be an A-side-rich compound, i.e. that lead to the mixed B-side, and i.e. the reactive side, not only through tuning of A-side, but the A-side also goes to B-side directly, and for the compound to form. And this is what we figured out in the end. And also because we open up the pores and the BET surface area also enhanced. So for this particular type of catalyst, this is what I try to bring up, highlighted. That is, besides the pores being generated, and we also have the uridine goes into the B side, i.e. A side metal go to B side. So this anti-side creation lead to a different performance later on, we think. So on the right-hand side, as you can see, this is where we propose the structure differences from the traditional pyrochloride structure with a A to B2 structure, right? So because this is a liturgy ratio between these two is a 3:2 structure, this actually under our synthetic condition for the porous generation, that turned out to be the most stable composition. Okay, so we're currently trying still to understand what is the thermodynamic origin for this type of structure. So our early assumption here is that by having the E-train substitution of B sides, literally we could create the oxygen vacancies, and that's going to be depending on the size of these two, right? So if you compare the far right on the top, this is the ruthenium, and this is the E-trains partially substituted case. So you can see that the bond length changes, and although this could lead to a different type of stability. So this is a study we're currently still doing it. So with that, we could further enhance the performance This is a geometric area, of course, to benefit from the opened up the pore structure to more context. And if you look at the tuffles, they also have some benefit of having this particular mixed B-side structures. So at that time, we also look at a specific activity based on the intrinsic oxide surface area. It turned out to be not that big. So we actually did not study this super hard about why the tuffle looks different, or whether we can utilize this particular aspect to further enhance the OER performance. But this is something that we're struggling at that time, and now it's lead to some of the recent study on this. To summarize, what recently people have developed a different kind of understanding of OER electrocatalysts, i.e. this including, I only select a few of these just to represent the very active research area of this field, i.e. the OER electrocatalyst mechanism based on the complex oxide system. For example, all these are based on electronic configuration, and whether they're using electrons or whether using the band energy to explain whether can use the oxygen hole in this type of configuration changes. It's all related to electronic configuration. The other aspect, of course, is the one I want to highlight it, is the lattice mobile oxygen mechanism. I think this one can continue attract people's attention to look into the function of oxygen in the lattice structure in the bulk, how that's going to be relevant to the activity and stability, and what's the role of oxygen in the oxygen evolution reaction. And this oxygen I'm referring to is the metal oxide or the complex metal oxide oxygen, right? So with that, I'm going to look into continuously saying what are the other factors we can tune to enhance the performance. One of them, of course, is the conductivity arguments here. And so one of the systems we tested is to use the tungsten as a dopant, and for example, calcium manganese system. So why we're choosing the tungsten, why we want to, let's say, dopant them, is that we try to see whether we'll be able to change the structure by having a certain amount of dopant and change the manganese oxygen overlapping and the configuration. So there are two different kind of considerations here. Oops, should be hypothesis 1 and hypothesis 2. So the conductivity could be determined by EG orbital electrons, for instance, and through these interactions. Also, it could be conductivity determined by T2G orbitals and through the bottom type of illustrations. And that's all related to the overlap between oxygen and the metal bonds. So by having the tungsten dope in the system, and this conductivity actually can change. So this is a summary of what we can do. So if you have a 1% and to 3%, this is the reported values. And what we figure out is that, in fact, in this particular system, if you try to maintain the phase pure system, we can dope tungsten to about 3%. For instance, if you look at this particular case for the calcium, manganese, and tungsten, either for example, perovskite type or the defect type of oxygen deficient perovskite type. Notice here the oxygen is 2.5 versus here oxygen is 3. And so this, if you have tungsten being put in, it can do up to reach about 5% without seeing the additional peak in this particular case. If you look at the shifting by doping the tungsten in this particular case, we see a slight shift, meaning that actually incorporate into the B sides in this particular case. And so what we have observed is the performance for the oxygen evolution reaction in both cases, whether it's the defect structure or the perovskite, they both get slightly better. And one of them is move much better than the others. Okay, so this is for oxygen evolution reaction case. It turned out to also happen to the oxygen reduction reaction. This is a polarization curve for this particular system. Of course, the number is relatively low, but it's not the key point. But the key point here is that the oxygen reduction and the evolution both being helped by the dopant. So that suggests to us experimentally it could be a conductivity improvement on top of the rest of factors, i.e. the other factor could be, for example, the valence change and through the, let's say, through the dopant. Okay, so that's another additional fact. But the key fact we think in this particular case is the conductivity through the dopant of the metal oxide particular system. Okay, so that says a lot about this particular system. Again, to summarize, the dopant of tungsten into this calcium manganate system to increase conductivities and remove the space charge layers. And of course, we're thinking of also the mobile oxygen could be a factor, as well as valencies. So these are the kind of hypotheses we proposed based on the known measurement before in terms of conductivity measurement and based on the known mechanism based on the electronic structure in that particular system. So in the remaining time, I'm going to show two cases that focus on the B-size tuning. So this is a size tuning in terms of improve the performance or improve the activity of this type. So the first one is the electronic structure, we think, that dominate the performance for this B-side pyrochloride structures in the OER catalyst system. So the particular one that I'm going to introduce you to here is this using the manganese almost at 50% dopant for the ruthenians. So this is probably another stories and another days. So to talk about the tolerant factor for the pyrochlorides, and just like for perovskite, there's also tolerant factors, and for the pyrochloride structures, manganese system happen to be the one that can have very large, let's say, ratio with the ruthenium without the change of the phase. So the synthesis is also quite generical. I.e., you can start with the Sol-Gel precursor and be able to create the EGM manganese ruthenium oxygen system completely in such a fashion. And the particle size is actually fairly small, less than 100 nanometer in diameter in general. So this is even without very careful controls of this particular system. So what we have observed here is that we can dial in the manganese at very different ratios. Okay, so in this particular case, if you look at the X-ray diffraction, so what we are seeing here, we can dial in the manganese all the way above 50%, the 0.5% in this regard, right? And so that leads to practically the 50% arrangement between these two sides. And of course, we can even move this further to 0.6. If you look at the X-ray diffractive peak, it shapes almost monotonically with the composition change. This is also being, let's say, examined based on the angle change, bound angle change, as a function of, let's say, the amount of manganese doping to that. And this also happened to correlate with the lattice changes as well. So if you combine all these information based on the Weger's law analysis, so this is good to form very nice solid solution type on the B size. So we can do this B size tuning in a very large degrees. So what will be the consequence in this particular case? And if you look at the per mass based analysis of this system, we can substitute the ruthenium, which is the rare earth metal, or the rare precious metals, and by using the 3D transition metal in a first row without losing activity. In fact, you normalize on the base side, and so it turns out at the around the 50% range, we can obtain the highest performance for this particular type. And so just to make sure the performance coming from the active side ruthenians. We also check the manganese side by itself. And if you purely use the yttrium manganese oxide, there's little activity that can measure. So that suggested to us the ruthenium is still the active side, but by introducing the manganese, we can effectively tune the ruthenium's reactivity in the OER reaction system. Okay, so this side tuning become quite interesting. So this is again the slide comparison, but using a different technique as well. Besides the comparison of activities, they reference the ruthenium oxide. We also did a comparison of stability studies, and this one as a typical 10 milliamp per square centimeters, it maintained a good stability as well. Okay, so this work I think we just got it published, and so if you're interested, I can probably send you the ePrint at some points. So one thing that we figure, we try to see which mechanism kind of helpful, and by a simple measurement of the hydroxide group on surfaces, and see whether that lead to, for example, anything to do with the oxygen vacancy. For example, all the valence of ruthenium has anything to do with this particular system. So if you look at this, what we have observed based on the XPS data analysis, we see the peak shift to high energies, and that's suggesting that the high oxidation state for ruthenium, which typically favor the mechanism of the AEM mechanism, right? So on the other hand, if you look at the oxygen vacancy part of it, so in this particular oxides, the complex oxides, and you see the fewer oxygen vacancy being created in that particular system, based on the preliminary study of this SPS analysis. So if we compare based on these type of arguments, that seems to us that in this particular case, the electronic factors is the dominant reason, is the main reason for the observed enhanced activity in this particular system. So not only one type, but in fact, that's the electronic features that did the most of the heavy lifting in this case. So again, so this summary kind of illustration of the effect we have hypothesized, i.e. this is primarily dominated by electronic structures, and the substitution by the manganese can lead to the bond distance, bond angle with the ruthenium oxygen bond changes. And this change we have two factors. One is the shortened bonds, the other is enlarged bond angles. Those two factors in the previous study demonstrated potentially you could have this downshape of the ruthenium orbitals, and that lead to a better overlap, and this actually lead to a better performance in this particular system. So this is primarily based on previous study and hypothesis based on the XPS data, XPS study that we have. So the second example, and the last one I want to mention here, is the reticent pulper phase, which can easily create the species that are relevant to the pyrochloride, the perovskites, and as well have the rock salt layer structure. So this is a different type of structure, but we want to demonstrate it. The mixed side, especially the active B sides, make quite a bit, quite important, and make the activity goes higher, almost quite routinely. That's what we have observed. So this is a case that I'm going to show you here. So just long story short, so this particular ones, you have this layered kind of like structure with the rock salt in between the perovskite, AB oxygen 3 layers. So you have kind of very nicely defined feature here. One of the other rationale to use this is that there is some studies suggesting depending on the kind of oxide we choose, if you have excuse me, loosely linked octahedral side and that tend to favor, structurally tend to favor the activity of OER. So if you have this highly shared, corner shared, cross-linked structure, they may not have the same kind of performance. So this is the work that being demonstrated in this particular reticent popper phase materials as well. So we try to look at, see whether if you create a mixed site again, so if a substitute is B side with partial substitution, what can we do, i.e. to continue to improve the valence change in that particular site and see what happened to it. Okay, so the same social approach being used in this particular case. We also see the peak shifted and with the composition change. And interestingly, even though these two have the similar tetragonal symmetry, but they have a slightly different phase depending on whether it's a ruthenium or the uridium in this structure. Okay, so this is the one that we kind of alluded to and think about whether they make a difference. So what we have observed, once again, is that right around the middle part of this, we start seeing the highest activities. Okay, so this is the one that we demonstrated in this particular series from 0 to the 100%, dialing between the uridium and ruthenium system. And if you have them in between, we have the lower TOEFL as well as the high activities. And all of these seems quite stable. If you do look at the the stability study at the 10 million per square centimeters, so much better than the ruthenium oxide case. Again, so in this particular case, what we have observed, because the structure flexibility and the possible, let's say, removal of the rock salt layers, we see a higher density of the hydroxide group on surfaces. And so that we think could benefit either mechanism. Okay, so in either mechanism, this high level hydroxide group is the intermediate state that could be beneficial to them. So that's what we think goes on in this particular case. And if we look into the composition tuning, what we think the major structure feature is that if we change the order to a disorder by using either uridium or ruthenium, because they have different bond angles in the corresponding pure phase, you created a maximum size distortion in this particular case, and that happened to lead to the maximum performance. So the specific reason that linked to this still need to be determined, i.e. whether the deep band, this was hypothesis, i.e. whether the broadening of band near the Fermi level, as previously, could contribute in this. This may need to have some simulation based on the quantum mechanism in the future. So that's beyond us. Another area that we are actively looking into is to analyze the surface structure in detail under the reactive condition, i.e. with the water moistures. So for that, so we are collaborating with two research group, Nicola Perry's group on the solid oxide part structure, the oxygen defect structures, as well as Dr. Klein from Germany on the surface study of these complex oxide structures. One of the unique area we are specifically interested in is to look at structure changes with without water. For example, if a clean surface compared with a clean surface and with water exposure, can we see any edge changes? What does this to do with the, for example, the band changes as well as the valency state for the metal involved? So this is something that we hope we'll be able to add to the overall picture of our OER catalyst. So hopefully on that note, I just summarize what I think that could be a very interesting, very dynamic and highly evolving area that is a complex oxide for oxygen evolution reactions. And because of the side tuning of A side and B side, remember they can have multiple metal elements in A sides and multiple elements in B sides that immediately offer us a lot of tunability. There are very rich structural parameter in design. So this could be quite interesting. The other aspect I want to bring it up is that unlike the conventional metal catalysts that we have paid a lot of attention to, I think it's a time also to pay attention to the oxygen, how does the oxygen be impact on the structure, i.e. the covalencies, the oxygen defect chemistry, what happened to do the surface and stability, and so on and so forth. So another aspect I pointed out through this talk is that partial substitution and doping of B side could have a effect, major effect in all our cases that being demonstrated here to improve the OER activities. And so another area is very active, i.e. the new theory is emerging almost continuously. And so I hope that's going to be attracting a lot of other people goes into the area and start to solve many of the complex problems and get to the best system we can with both activity and stabilities. So on that note, I would like to thank my student. Most of the pyrochloride work has been done by Dr. Chen Jiang, Dr. Jimmy Kim, and part of the work is done also by Page Shen, and also Fang Fang and Maria Barton and Jim Kung Han. And they also have different aspects of this OER catalyst. And so some of these people at the bottom here involved in the OER catalyst as well as the nanoparticle synthesis. And this particular work primarily supported by the National Science Foundation of United States from the CBAT division. So on that note, I'd like to thank you for your invitation and thank you for listening. Okay.
Okay. Thank you very much. So thank you for excellent talk. And
right.
It introduced many OER catalysts with a different composition and different morphology. And I understand that the very good tunability of the metal oxide catalyst. So okay. Oh yeah. So it's almost close to the 10, but let me have 10 minutes for discussion part. So okay. So I found oh, Alex. So can you speak in your microphone? Oh yes.
Is it okay? Can you hear me now?
Yes, yes. Now I can hear you.
All right. Thank you very much, Professor Yang, for this very interesting presentation. And of course, I've heard some of your work already before. My question, I have several questions, but the first question I would like to ask you is about the Rödsten-Popper catalysis, where you didn't touch the topic of the interstitial oxygen. So Rödsten-Popper phase oxides are known for being able to host additional oxygen in the rock salt phase. And that can be a possible reason for further tuning the catalytic activity. Have you looked at those properties?
Yeah, at the moment, we haven't really studied that activity in the level, at the level that you are alluding to. One of the reasons is this catalyst, the stability side is an issue. So in fact, it turned into a structure that's more complex than we originally thought. So this is our first work in the Rödsten-Popper phase. And the OER, once it started, and it's actually turned into a different phase. So it's become very, very interesting. So so it turned into metallic, in fact. So that's something even more interesting than I originally thought. So we're looking into it. You're correct. So the original structure is not the end structure for the performance that we're looking at.
And I saw in many of your explanations today very nice theoretical models, but all those models were based on very perfect surfaces, which more or less look like cleaved bulk phase. But those oxides might tend to severe surface reconstruction. So then, of course, the catalytic mechanism will look differently once the surface does not look really like the bulk phase. So did you focus on studying on how those surfaces change during the reaction conditions?
Yeah, I'm gonna have to rely on you to contribute to this project in this nature. So my comment on the simulation part is that we do need a lot of work. So one of the reasons we went back to propose to study the surface, the dynamic surface in particular, is precisely what you just mentioned, i.e. to understand what will be the structural features on the surface. But one thing could help is, what if that structure is stable? So clearly you're correct. So all the crystalline structure will not be the real case for sure. So that I can be sure. But once you introduce the defect, and then that's something that the simulation could potentially helpful. But for oxide, it's tremendously challenging. So that's why we ourselves only did one simulation is based on the ruthenium yttrium ruthenium oxygen system. So we only look at the stability of ruthenium oxygen bond length and the overlap, how that could contribute to the bond stability. In terms of activity, I agree with you. It's tremendously challenging and to get a good handle of it. But we hope we'll be able to kind of try to understand what will be the structure, let's say stable structure trend in those systems, and then we can potentially be able to apply DFT. I agree. The DFT has a limited, in my opinion, okay, limited. Let's say, how do I put it? I have to be sensitive here.
It needs a good model.
That's correct. Okay, let's put it that way. Just a tremendous opportunity, but also very challenging to get a real good model to really understand the system. Hopefully, be able to guide the experiment design. Yeah.
Thank you very much. And I have many other questions, but I'll ask at another point. Thank you.
Okay, great. Okay, thanks. Nice meeting you, Alex.
Okay, thank you very much. So yeah, you can raise your hand button if you have a question. Is there any question?
Yes.
Oh yeah, Petros.
Yes, Professor FY2022, I have a question.
Oh yeah.
Of course, I can ask this question to Hong.
All right.
Anytime, but this is a good opportunity. This is a very general, perhaps strategic question, Hong. As you know, now we have the hydrogen earth shot, right? And we all try to produce cheap hydrogen, right? In fact, the Department of Energy wants in 10 years, by the year 2032, right, to produce hydrogen at a cost of $1 per kilogram, right, which is about 100 yen per kilogram of hydrogen, right? Professor FY2022, am I right? This is about the price that the Department of Energy is aiming at, right?
Okay.
$1 per kilogram. I think, of course, this is a noble target, right? If we get this price, then the hydrogen economy is there, right? Then we can create off-takers, we can create markets, we can create demand. Now, today, in general, hydrogen is expensive. How this research that you presented, the evolutionary action that you've been telling me, this is the bottleneck, right? What do you think? Can we get there in 10 years? What are the prospects? Since you are the expert, please give us your accumulated wisdom here. When we get asked this question, where is hydrogen economy? Where is it yet? Based on this price of hydrogen.
Yeah, okay. So in fact, the price is just one issue for the green hydrogen production. So you probably well aware of the cost scale with the different color coded hydrogen production, right? So there's this gray hydrogen, right? So they also have the hydrogen generated from methane, right? Direct carbonize it and produce hydrogen at the same time. And those are all different versions of the hydrogen that being proposed in the DOE scheme. So the green hydrogen is probably the most expensive one. But if you want to make impact, at least that's what DOE tell us, right? So from their technical economic analysis, all things considered, so we are relying on the electricity cost, right? So the route currently being floated around is that can we utilize the cheap or even negative cost electricity to generate the green hydrogen using, for example, other energy source, i.e. the nuclear high temperature system, and using those energy as the sources for the hydrogen generation. So those are all kind of different values. So certainly the $1 goal is probably going to be, hopefully if it can be reached in the targeted time period, probably has to be the a la carte scheme first. But the green hydrogen is part of it. One of the major hurdle even for green hydrogen production at the moment is actually the use of iridium. How we can replace the iridium in our system. And that's something under the acidic condition, that is. So that's something that people work pretty hard to get the let's say the handoff. And so my impression is that there are some systems demonstrate enough stability. For example, the most recent example is the spinel structure. So those systems could potentially lead to, let's say, at least lower, let's say, iridium costs, lower iridium usage system. That's what I think in terms of the water electrolyzer, the major pain point. And DOE focuses more on the iridium-free system rather than the cost cutting in this particular area. I hope that partially answers your question.
Yeah, certainly.
Yeah.
Because I received this question from various stakeholders, right, from industries, etc., and they are asking me how your institute, I²CNER, can help us. Where is your science here to reduce the cost of electrolysis? Because they are interested in green hydrogen, for instance, environmental groups, right? Environmental justice groups, they want green hydrogen. Yeah. This is the target they are asking for. And since we are a carbon neutral institute, right, the question that I receive is how you, the scientists, can help us reduce the cost of electrolysis.
Yeah, the cost cutting in terms of the system level, also the catalyst level, has achieved a tremendous progress. So my understanding is that by considering all the system, the catalyst cost itself only become a relatively small portion of the whole system cost. And it's really become the electricity cost and also the availability of all the rare metal, the precious metal, let's say, reserve. And those are some critical aspect in terms of green hydrogen production.
Okay, thank
you. Yes, we have a responsibility to answer these questions. Yeah.
Yes, we do.
Yeah. So yeah, any question? I can accept one more question if you have. If you don't have, I want to ask question, but okay. Yeah. So yeah, Professor Yang. So I have a question that you showed. I want to back to the scientific part. So
right.
Yeah. So you showed the porous yttrium ruthenium oxide catalyst.
Right.
So it looks very nice, but I want to ask conductivity, electrical conductivity of this material. So
it's still insulator, unfortunately. So we have to rely on the conductive let's say, powder in between to do the measurement. So at the moment, And so that's why in the first phase, we also try to do the tungsten dopant, but it's still not good enough at the moment. Yeah. So the improved conductivity certainly is another important aspect for the future development of this specific type of, i.e. the complex metal oxide catalyst. There's some solution to it through dopant as well. And so you just have to choose the right dopant, and that can have the high, let's say, high rate of incorporation, i.e. the tolerance factor is higher than the system we have. So far, there are some system that has showed the sign that can be done, but not this particular case.
So finding the good dopant is an issue in this area.
It is I think so. Yes.
Okay. Thank you very much.
Yeah.
Okay. So yeah, it's already 15 minutes past behind the schedule. So if you don't have a question, so I want to close this seminar. So again, thank you very much for Professor Yang. It's very good time to study, and also good time to look at your face in the camera.
Okay. All right. Thanks again, Professor Fujigaya, for hosting the seminar. And thanks, Petro, for the invitation. Okay. All right.
Okay. So thank you very much for audience, all the audience.
All right.
Yeah. Bye.
All right. Thank you.
Have a good night.
All right.
Good morning.
Yeah.
Professor Fujigaya. I think having a great morning, productive morning.
Yes, it is. So thank you very much.